Okay, binary conversion. Binary conversion is a very common question at the beginning of exam papers. They're often worth 1 or 2 marks, but sometimes the questions will be worth, there'll be several parts to them rather. First thing that we need to know is that it's a counting system. It's not a particularly difficult counting system. In fact, it works in the same way that a denary counting system works, in that once a column has exceeded its maximum value, it spreads into the next one. And that sounds a little confusing, but if you think back to when you were in primary school and you learnt about units, tens, hundreds, etc., once the units gets to 9, and we want to go 1 higher, we cross this out, replace it with a 0, and write a 1 in the tens column. What this means is we've counted to 10 once, and this will happen again when we get to 19 and we want to go to 20. We'll cross out this 9, write a 0, write a 2. Binary works in the same way, except you're going to have 1s, 2s, 4s, etc. And once you've got to 1, to get to 2, you're going to need this, and then to get to 3, you will need this. So you're just flowing over into the next column. And that's it really. Typically speaking for GCSEs, it'll require 8 bits. Not always, but generally. So probably more than our 1, 2 and 4 column. A-levels might be a little different. They might try and hide the information within some distractor elements of the question, but if you can do the conversions, you're often going to be quite well set with these. There's no reason why you can't get these right 100% of the time. So let's look at an example. Here we've got an 8-bit system that will be quite common in the early stages of an exam. And what I would recommend that you do is that you write the column values in. Now you need to remember that you start left to right with the biggest values on the left. So in this case, we've got 128, 64, 32, 16, 8, worst 8 ever, 8, 4, 2, and 1. Now if we had a 9-bit system or a 10-bit system, all you'd do over here is you just keep doubling. Okay, so the next one would be 256, 512, etc. So now we've got that, all we're going to do is add up the values which have got a 1 under them. So we've got a 1 here, so that's going to be a 64 plus a 32. We've got no 1s here, we've got a 2 there, so plus 2, and that is going to give us a total of 98. Okay, so that's that 8-bit system, relatively straightforward. So we've got another one. This one has a couple of leading zeros. Now when you write this sort of thing, sometimes you might choose to leave those off. That's absolutely fine. But for the sake of it not being too confusing, I would often encourage you to leave them in. It will mean that you always count the right number of bits and so on and so forth. Anyway, here we don't have any 128s or 64s, but we do have a 32, 16, no 8s, a 4 we do have, a 2, and a 1. So here we're going to do 32 plus 16 plus 4 plus 1. And this is going to give us an answer of 53. Now, what do you notice about 53? Well, I notice that it's an odd number. If we go back a page, 98 is an even number. Why am I bleating on around this? Well, it's because this bit here is the indicator of whether it's odd or even. If we're aiming for an odd number, this one should be switched on. There should be a 1 here. If it's an even number, then it should be a 0. This is handy whether you're trying to convert from denary to binary or whether you're trying to convert from binary to denary. It's a nice way of going, yeah, I'm probably got this right. Here, we've got a 0 indicating this is an even number, and 98 is also an even number. It's not a dead cert that we've got it right, but there's a good chance. Here, we've got a 1. That's telling us that this is an odd number. 53 is an odd number, so again, we likely have it right. The other thing that can happen is you can be asked to do it the other way around. Now, I'd still encourage you here to write in your columns 4, 2, and 1. But we're going to approach this differently. We're looking to get 120, so it's a relatively large number. It's a good way off, actually, the maximum value that we can represent here, but it's quite a big number. And what we're going to do is we're going to go, well, does this fit into this? Well, the answer is no. So we're going to write a 0. 64, on the other hand, 64 does fit in there, so we're going to write a 1. And what we need to do is take 64 from 120. So 120 take away 64 leaves us with 56. Does 32 fit into 56? Yes, it does. Okay, so now we've got 56 take away 32, and that gives us 24. Does 16 fit into 24? Yes. So we're going to do 24 take away 16, and that's going to leave us with 8. 8 obviously fits into 8 perfectly. 4 doesn't fit into 0, neither does 2, and neither does 1. Okay. Now, you won't always have to approach it this way, but I would encourage you to come up with a system that you do every single time. Okay. There's a couple of tricks that you can look for. If it's a very large number, then maybe you could do it the other way around, so you could subtract things from it. You might look at it and just sort of know, right, okay, if I add 1, 4, and 32 together, I'm going to get this number. But generally speaking, you want to try and be systematic with this. It'll avoid mistakes. So let's take a look at an exam question. This particular exam question comes from the Cambridge exam board. So this is from the IGCSE, but same principle. What this question is asking us to do is to work out which of these numbers over here correspond with these numbers over here. Okay, and there's some easy stuff that we can do to get us started. This is an odd number. Oops, funny way of writing odd. This is an odd number. Okay, and so is this one, so is this one, and the others are all even because they end in a 0. Okay, now this one is way too small. That's 32 plus 1, so that's 33. So it's not this, which only leaves us with this one. You can work it out, but this is 32 plus 8, which is 40 plus 1. But it's actually not necessary. In this case, it can only be one of those two, and we know it's not that one. So 41 goes here. 124 is a bit more difficult. We're not going to worry about that one for a minute. We're going to look at 86 next. Okay. Now, 86, relatively large number, but we know it's not going to be this one because 128 is too big. We know it's not going to be this one because 128 is too big. And it's also not going to be this one because 128 is too big. 33 is too small. This one's taken. It can only be this one. So we don't even need to work this out. This is process of elimination stuff. It's that one. So 174, well, it can be this one, or this one. And there's no clever trick. That's what makes this one a little bit more difficult. Okay, it's more difficult to narrow down. So here we've got 128 plus 32. And this is going to put us in the region of about 160. Fine. And here we've got 6. Well, I know it's not exactly 160 perhaps, but this doesn't feel like it's going to add up, right? It's certainly low 160s. Just working this out roughly, it's not going to be that one. It's unlikely. Looking down here, we've got 128 plus 6. Well, 128 plus 6 is a long way off 124, so it's not going to be that one. So then we've got this one here. Okay, now this one here seems very promising. We've got 128, and we've got 32. That gives us 160. That's nice and easy. We've got an 8, which gives us 168. We've got a 4, 172, and we've got a 2, 174. So it's got to be this one here. This is the one. So there we go. Okay, so that's how you work through that particular style of question. Notice 3 marks, and actually you don't have to work every single one of them out. 86 we did with the process of elimination, and 41 also is a sort of a process of elimination. Right, let's take a look at another example. This one comes from the Cambridge exam board again, and you'll notice it's using 12 bits. Okay, but actually this is a little bit of a con because these 3 bits here are not being used. You should remember that it's using 12 bits because if this was the other way around, for example, they might want it displayed as a 12-bit number. But in this case, we're actually only dealing with 9 bits. If we write that number out, 1, 0, 1, 0, 1, 0, 1, 1, 1, and then write our column values in 1, 2, 4, 8, 16, 32, 64, 128. We double it one more time, we get 256. All we have to do is add those up. So that's going to be, oops, let's do it over here, 256 plus 64. Well, 256 plus 64 gives us 320. So I'm going to make a note of that. Do it down here. 320. And we want to add 16. Gives us 336. Then we want to add that 7. That gives us 343. Okay, now in this case, there are 2 marks available here. So it is highly likely that they're awarding 1 mark for your working and 1 mark for your answer. The other way that this might happen is if it was convert 343 to a 12-bit binary number, they might give you marks per nibble, for example, so marks per group of 4. You want to be aware of the number of marks and how they might be awarded, because it should make a difference to the way that you display things. The examiner should look for the mark, right? So the fact that I've written all over the place but not really used the working out space doesn't matter here. But you should bear in mind that you want their life to be as easy as possible. So try not to clutter things too much, try not to cross too many things out. If you need to, ask for a spare piece of paper. Right, final example. This one's actually taken from the British board OCR, and it has a few different things that we need to do. First of all, we need to convert this binary number into denary. So we're going the other way around here. So here we've got 1, 1, 0, 0, 1, 0, 1, 1. So we've got 128 plus 64 plus 8 plus 2 plus 1. We know this will be an odd number, and if you add all of those up, it comes to 203. So that's my answer right here. Okay. Next, they want you to complete a 2-place shift to the right on the binary number 11001011. So what I would typically do here is 1100 1011, and then we're going to add 2 zeros to the start and cross these 2 out. Okay, not my neatest job, but you get the idea, right? And that's the answer, that's your 1 mark. Now what you've actually done is you've taken these bits, which were 128 and 64, and you've moved them 2 places to the right. That's our 2-place shift. Okay, so they're now worth 32 and 16 respectively. But we're still dealing with an 8-bit system, so we have to drop 2 of them off the end, which is the 2 that I've crossed out. Okay. Lastly, we've got explain the effect of performing a 2-place shift to the right on the binary number 11001011. So if you work this number out, this one here, that's 203. Okay. If you move everything to the right 2 places and work that out, that would be 50.75. Now this 75 gets lost. In fact, some of this might even get lost because we have lost some information. We've lost these 2 bits off the end. So one of the effects is a loss of accuracy. Okay, that is one of the problems that happens here. The other thing that you will notice is that 50 is approximately a quarter of 203. I say approximately because we've lost some information. So what we've actually done here is we have divided by 4. And that's your answer. Okay, so to summarize, the conversions themselves, I hope you would agree, aren't too difficult. If you're going from a binary number to a denary number, all you're doing is adding up the column values each time you see a 1. If it's the other way around, you want to continuously ask yourself the question, does this number fit into the number I'm trying to convert? Lastly, we looked a little bit at place shift here. Incidentally, if it was 2 places to the left, it would be multiplying by 4. Okay, you'd still have that loss of accuracy, but instead of divide by 4, it would be multiplying. Right, I hope you found those examples helpful. Thank you very much for listening. Goodbye.